Okay. So this is for my reference. Okay, let it be. So first, today we want to do Radon Nykodym theorem and something else. Okay. So this was stated yesterday. This was used by Divya yesterday in his proof. So before the stating that, we want to prove the following. We want to notice the following proposition. Okay. So let some measure space. We have some measure space. I mean, when I say just measure, it is just a positive measure. Okay. When it is complex measure or real valued measure, I will say that. This is just a measure space. I mean, no, let me say that. So, we have some measurable space like this. Okay. And mu. Oh, we are not going. We are having only one measure, sorry, for the time being. This is a measure space. And f from x to 0 infinity is a measurable function, is measurable. Okay. With, I mean, f takes infinity only at finitely many values. Okay, why do we need that? Let's see whether I may not need that. Let's see. Well, we anyway need it. I mean, okay, it's not needed. Let's see. Okay, then define mu of e equal to integral over e f d. Okay. Then mu is a sigma finite measure space. Mu is a sigma finite measure. Okay. So proof. I mean, we only have to see that the integral is defined. Integral is anyway defined for any such function, and because f is non-negative, it's well defined, and that implies nu is positive, and nu of phi is 0. Nu of phi is 0, and nu is countably additive due to MCT. Okay. I mean, we have applied this earlier, thanks to monotone convergence theorem. I mean, if you want to have a set, you are going to write like this. Sorry, this is En. Okay, that's going to be. I mean, this is also equal to omega f1 d2, okay. And you are going to have this. Now you have En d, and that you can just. It will be just the limit of that, and it's an increasing limit. So it's clear that by monotone convergence theorem, sorry. Right. So it follows from by monotone convergence theorem that this is a countably additive. So only thing we are left is to prove that nu is sigma finite given mu is sigma finite. Okay. So let x equal to union of xn. Okay. And En equal to all those x in xn such that mod there is no need for mod because it's positive. F of x is less than or equal to n. Okay. Then union of En is also equal to x, and mu of En is finite, such that mu of xn is finite. Okay. So because mu is sigma finite, we can write x as union of xn with mu of xn is less than infinity. Now we define En to be like this. We further impose one more condition on that. You take x in xn such that f of x is less than or equal to n. As n increases, this f of x will take all its values. Up to till infinity, and this En will increase to x. Okay, and nu of En is because f of x is less than or equal to n, so this will be n times nu of xn, which will be final. Okay, it's clear. It's final. So because of that, it follows that nu is also sigma. This is clear. So given any mu, given a measure mu and a non-negative function f, we can.
Sir, f can also at an infinity, right?
F can take value infinity, yeah, sure.
But then how is the union of En equal to x? And how is infinity covered
there? Okay, that's why you have to add that set finally. You have to add that set also. No, so that is where the problem comes, no? Maybe that's why I need. If it's infinity, if that set does not have measure, if it has measure which is suppose if it has measure something which is greater than 0, then it may be a problem. I don't see why. Okay, we don't need this because we will get a real valued function. We'll take real value. Okay, I think it has to be real value. I thought we can take the value infinity. It's real because we will prove that it has real value, so it's okay. We will get a L1. We will get a function which is L1, integrable function anyway. So the value it takes in. The set where it takes the value infinity has to have measured 0 anyway. So it's okay. Yeah. So this is fine. So we will consider only the functions which does not take the value infinity. Which takes the which is almost surely it takes the value. Almost everywhere it takes the value a real number. Yeah, this is fine. So we don't need infinity. Okay, fine. Because we will get a L1 function. When we prove the converse, we will get an L1 function. Okay, so that's all. So given a function, non-negative function, and a measure, we can build up another measure nu, and this measure satisfies the following. Maybe I'll write it here, which is clear further. Mu of e equals 0, then mu of e equals 0 implies mu of e equals 0. That's clear. If you integrate it over a measure of measure 0, then it is 0. Okay. So this is what we call as dominated by this. We say a measure mu dominates nu if mu of e equals 0 implies mu of e is also equal to 0, and denoted by, we denote by nu is less than or equal to mu. Okay. Or mu is which way it is? Mu is absolutely continuous with respect to mu. Or mu is absolutely continuous with respect to mu. Is also called mu is absolutely continuous with respect to mu. Okay. So this is the theorem we want to prove, Radon Nykodym theorem, which is the converse of the first proposition. Okay. This is what is called Radon Nykodym. Okay. So if nu is absolutely continuous with respect to mu, then there exists a f in L1 nu, f is non-negative such that nu of e equal to integral over e, okay, for all e. So these two measures are on the same measure space xf. On that, so we are proving the converse of the proposition. This Radon Nykodym, this theorem was stated by Divya in the last class, and we are going to prove this. So if you have one measure mu which dominates another measure nu, in the sense that if mu of e any set is 0, then nu of e is also 0. Then it is actually given by whatever the prescription in the first proposition. Okay. So
throughout, sir,
yeah.
throughout are we like having the assumption that like all measures like given are sigma finite?
Exactly. All our measures, when I don't say anything, it's all sigma finite. Okay. Mu, nu, sigma finite. Sigma finite. Okay. So even if I don't say, you should assume that. Okay. We are not dealing with non-sigma finite measures. Okay. I mean, usually in real life, there is no use for non-sigma finite measures, but we cannot completely ignore them, in the sense that there are, in physics, for example, there is a non-commutative analog of measures, which are called states or weights or something. I mean, on operator algebras, when you study I think I will, in the next semester, I will define operator algebras, where we will study states or something. Or here we will, I mean, the next class we will study something called a state. I will define what it, I will not define explicitly a state, but whatever I am considering is a linear functional, positive linear functional, which has, if with some property, it will be called a state. But there, those weight states are linear. I mean, the analog of measure, non-commutative analog, are linear functional, positive linear functional. And there are positive linear functional which actually which are not analogous to sigma finite measure. They are the one appropriate in physics. See, there is something called type 3ness. So we cannot completely ignore sigma finite measure. But in real life, in probability or anything, whatever we do in our mathematical setup, there's non-sigma finite measures are not significant. I don't know what statement I made, but this is what I want to make. Maybe I am, instead of non-sigma finite, I said sigma finite in my previous statement. But what I want to say is, we don't usually deal with non-sigma finite measures in mathematics. But in physics, in the non-commutative analog of measures, which are the positive linear functional, we have already seen what are linear functional. So there is something called positive linear functional, which I will define in the next class. So there, the analog for non-sigma finite measures are very important. So you cannot completely ignore them. Anyway, that's a different issue. So we are only dealing with sigma finite here.
Now, what do you mean by non-commutative here, sir?
Not here. I said non-commutative analog of measure, which are linear functionals, I said. Which will be clear in the next class. It will be clear.
Okay.
I will tell you in the next class. Okay. Ask this question again. I will tell you. Okay. No, I am just saying that it's not completely we can ignore non-sigma finite measures. It has some meaning. I mean, it has some relevance. That's what I want to say. Okay.
Okay.
Okay. It's just a remark. Okay. So we want to prove. So it's 521. So we want to prove this Radon Nykodym theorem. So to prove that, we will use the Riesz theorem, Riesz lemma, which we have proved proved for Hilbert spaces. That we will use. Okay. So we define a new measure, which is just mu plus mu. Okay. We can add two measure and form a new measure. Form a new measure, which is possible. Now we define a linear functional phi from L2 of rho to C by phi of any f equal to. So here I am taking. I mean, this is not exactly linear functional. XD. This is a conjugate linear functional. I mean, it's a. I said anti-linear. No, it's a scalar will come out as a bar. Okay. So this is a conjugate linear function. phi is a or anti-linear function, conjugate linear function. I mean, a conjugate linear functional, there is nothing complicated. You just take a bar, you will get a complication linear functional. And if you have a conjugate linear functional, you take the bar, you will get a linear functional. Okay, there's a one-to-one correspondence between them. Okay, so whatever the reason, so here I'm taking the bar f bar because I want to get this. Okay, so maybe I will slightly change this. I will take a h here because I will use f here. I use h here. Okay, I'm just change the f to h. So we have Rees lemma, which says that every linear functional so this L2 row is a Hilbert space, and every linear functional on a Hilbert space is given by inner product. Every linear functional. So if you take a conjugate linear functional, it will be just the inner product will be twist shifted. I mean, it's in the conjugate linear space. You will have the element of the Hilbert space. Instead, you will have the linear space. I mean, the first place. Okay. So we have to prove that it's bounded. Okay, so we take mod of this, okay, which is equal to mod of omega. So I see this is the problem with omega. I'm using x. In the first class I used x, so I'm still continuing with that. Okay, but in the book everywhere it's omega. So I may sometimes use omega, but it is x. Okay, don't get confused. Okay, so this is f bar d mu. And there is a Cauchy-Schwarz, I mean, whatever, which is the other form of Holder's inequality or something, which is same as Cauchy-Schwarz, which is less than or equal to, which is less than or equal to, I mean, this is f times 1, or you can write it as, if you wish, this is just mod of inner product between 1 and f, okay, in L2, okay. I mean, this is not the inner product in L2 row, this is L2 nu. So this is less than or equal to 1 is a function. I mean, if you integrate 1 over this, you will get nu of that x whole power half times norm f2. Norm f on L2. Okay. But then we have, norm of, this is the norm in L2 nu with respect to the measure nu, but the rho is a bigger measure. Okay. I mean, it's just a sum of that. So the L2 norm will be less than that. This is less than or equal to mu of x power half times norm f L2 rho. Okay. So phi of s is bounded. This is the bound. Okay. So this implies phi is bounded, but it is conjugate linear. So by Rees lemma, which is just the conjugate version of that. Say you can use f itself here. Instead of f bar, you can use f, but then you will get h bar or something. I mean, which instead of that, we want to get the right thing, so that's why I'm using f bar. There exists a h. Maybe I will have to change this to g or something. It's okay. We will get finally some. Maybe I'll write this as g. Okay, there exists a g in L2 row. Okay, such that whatever that phi of f equal to integral f bar d nu omega x equal to, so the inner product between them in L2 row. Okay, let me write that inner product between, here I will get that element. So that element is g and f. Okay, gf in L2. Okay, because we have proved it's a bounded conjugate linear functional in L2 row. Okay, so equal to this, which is equal to integral over g f bar, okay, d rho. Okay, this is fine. Okay, so we have this inequality. Okay, integral f bar d rho equal to integral g f bar d. Okay, but then rho is mu plus, this is equal to x, g f bar d mu plus d mu. Okay. So this implies integral over x 1 minus g of f bar d mu equal to integral over g f bar d mu. Okay. So we have related nu and mu by this integral equation. Okay. Now let's take for if f is, so this is all f for all f in L2 of rho. So if f is greater than 0 and bounded, okay, then f is in L2, any L2. Okay, because let's assume a rho is mu and mu are finite. Okay, case 1 for the time being, mu are finite measures, and we can extend to sigma finite measure by taking different f finite measures. Okay. So f is non-negative and bounded, so then it is integrable, of course. Then it is in L2 because it's a finite measure. Any bounded function is integrable. So because of that, then for this, then f bar is just f. Okay, then we have this equation: integral over x 1 minus g f d nu equal to integral g of t. Okay. This is for all positive bounded function. Okay. Okay. So first I want to prove that f is non-negative. Okay, f is non-negative because right. So here itself I can find f is non-negative. So here this equation, which I call it as g or some star or something. Okay, by take f bar f equal to 1 e for some e. Then that implies that integral over g. I mean, if you take 1 over these, then you get nu of e. Nu of e equal to integral g d rho. This is greater than or equal to 0. So g is, I mean, g when integrated over any set is positive. Okay, then g is positive. I mean, this is same as what I asked in the exam. If you integrate a function g over every set, it's positive, then g is positive. It is clear anyway. I mean, you take, suppose g is not positive. So not, I mean, g is positive means positive almost everywhere. Sorry, almost everywhere rho. Okay, hence almost everywhere, because mu is a smaller measure, almost everywhere mu. Okay. This is because suppose if we have a set with positive measure where f is g is negative, then you just integrate it over that set, only over that set. That set, you will get a negative number, which is the contradiction. Okay, so that's why. So this is true. Okay, this follows. So we have proved it's non-negative. On the other hand, consider this equation, which I call it as double star. Okay, okay. Here I want to take something else. So here, what do I do? So here I want to do the following. Okay, so here also I want to substitute something for f. So now take some set a equal to this x in x, such that f of x is greater than 1 or less than 1. So not f. G of x is non-negative, so greater than or equal to 1. A equal to. Okay. Then, so, and we have to substitute for f. G is fixed and f is varying, so f equal to 1a. Okay, in star, in that equation, substitute in the star equation, which is this equation. You just substitute f equal to 1a. Okay, then so what is this? This is just 1 minus g. G is greater than or equal to 1 on that set. Okay, if you take g equal to 1a, then in that set, I mean f equal to 1a, sorry, f equal to 1a, where on that set, so this is left hand side will become integral over a and then 1 minus g, which is just g is, I mean, which is just negative. Okay, 1 minus g f d mu. I mean, which is just minus g d mu. Okay, and this is less than or equal to 0. Okay, this is less than or equal to 0. On the other hand, if you take that, that is going to be the right hand side is equal to, I'm taking g equal to, g is integral g over a d, which is negative. But then this is g is greater than this, g is greater than 1. So this is, I want to say something is positive. So which is positive? G over this. G is greater than, g is greater than or equal to 1. So this is greater than or equal to mu of, this is greater than, I mean, g is greater than or equal to 1. So this is greater than or equal to mu of a, right? Which is positive. Okay. So something is, I mean, this is mu of, I mean, mu of a is positive, which is less than or equal to this, which is equal to this, which is negative. So these things implies mu of a equals 0. The set where g of x is greater than or equal to, that is mu of set g greater than or equal to 1 is 0. That is g is less than, we have already proved it's greater than 0, less than 1, almost everywhere. Okay, that's what it means. Is this fine? Any questions? Is this fine, sir?
Yes, sir.
Is there a problem? I have just substituted, I have taken a set A where g is greater than or equal to 1, and I just take the indicator function or characteristic function of that set A and substituted in that equation. Okay. Then on the one hand, I get this is greater than or equal to 0. On the other hand, I get it less than or equal to 0. Okay. So it has to be equal to 0.
Okay.
So because of that, this is,
Okay, sir. Yeah. Yeah, this is fine.
so because of that, we have that g is less than or equal to 1 and greater than or equal to 0. In that, I mean, in particular, we can have 1 minus g. You can divide it. 1 minus g is not equal to 0. So you can divide it by that. That's all. Now take, okay, that's what I have done. Okay. Now take, so in particular, what happened is we have this equation. We have this star, double star. Okay. In this, so g is strictly less than 1, almost everywhere. Okay. So this is positive. On the other hand, g is positive. Okay. So, I mean, so f is positive. F is also, I mean, suppose f is positive. Okay. What I am saying is by MCT, see, we have this equation, double star, which is true for all non-negative f and bounded f. This is true. And g is positive, 1 minus g is positive, because whatever we have proved. So if you have a non-negative f, the whole thing is positive. The integrand is positive on both sides. And the integrand is bounded. Okay. Now you can cut f by n or something and then consider the truncated f. And by using MCT, you can have, this equation holds for any f. That's what, even unbounded f. That's what I'm saying. Okay. By MCT, star holds for all f greater than or equal to 0. That is this. That's what I'm saying. Integral 1 minus g f, right? 1 minus g f d nu equal to integral g f d for all f greater than by MCT. That's what. Just to apply MCT, I am just using that condition. Okay. Not just that, we can divide it by this also. Now you take a function, a new function, call it k or something, let or f itself. Sorry, f equal to. So now take f equal to a new function k by 1 minus g. Okay. So just substitute it. Then what do we get? We get integral over f. Sorry. So if you apply k by this, you get k integral k d nu, any function, equal to over x equal to integral over g k by 1 minus g k, right? That's what we get. Okay? Yeah. Now take k equal to 1e for any e. Okay. I mean, we have something more also, and okay, g by 1 minus. Then you have equal to h d, right? Over. This is fine. We have got a g is greater than or equal to 0. Okay. It's fine.
Sir, I had a question where you use the Rees lemma. Yes, so like the Rees lemma, I mean, works for only functionals, right? But this is an antilinear function. So how exactly did you conclude that?
No, you have, I'm just, see, Rees lemma says that if you have a linear functional phi, then phi of x equal to, there exists a y such that xy. Now you take a bar.
Yeah, but this was an antilinear. Oh, okay,
all.
that way.
That's
okay.
Linear and antilinear, you just have to use a bar. That's all.
Yeah.
So you the x and y will be interchanged. That's all. Okay, so I think this is proved. There is no other problem, and we have just proved. Okay. Okay. So this h is what is called Radon Nykodym derivative. H has the notation. H is called Radon Nykodym derivative of nu with respect to mu, and it is denoted by d nu. Oops. Denoted by d nu by d for reasons, well-known reason. I mean, it is just if you want to integrate. See, because since, and this is clear, if you have a radon, see, if this is true, we have already proved that anyway. But if this is true, then this equation implies integral over any f d nu equal to fh d mu. That is just check for simple function and then take the limit. It will be clear. It's clear. Okay, because of that. So since if you take any integral f d mu equal to integral over f d mu by it should be the other way, sorry, f d mu equal to that's right, no? Is d nu by d mu, right? Yeah. So it's just d nu by d mu expression. Right? This is the function. This is the function h we have used. Right? So it's because of that. This is what is called derivative, which you know the integral. And the properties of this is note. If you have three measures, okay, if you have lambda is less than or equal to mu, less than or equal to mu, okay, then and another thing is it's unique. I mean uniqueness. Sorry, I forgot to say the uniqueness. Radon Nykodym derivative is unique. Radon Nykodym derivative is unique. That's because if there are two, I mean, since integral over fe equal to integral over ge implies for all e implies f equal to g. No? I mean, if you that's the problem in the exam. If you have a function which vanishes integral f over all sets are 0, then f is 0. I mean, that is just you take where it is. I mean, if it is not 0 somewhere, then it's positive somewhere, negative somewhere, then the positive part should be greater than 0. I mean, if you take the where it is positive, strictly positive, there you will have you just integrate it over, you get a positive number. So it cannot be 0 everywhere. Okay. So because of this, the Radon Nykodym. So because it's given by that integral, yeah. Say it again. Someone said something. So because the integral, I mean, because the integral over all
finite measures.
Finite measure, yeah. Oh, you have to say that. Oh, I forgot to prove for sigma finite. That is just you have to take the. I mean, okay, we have proved for sigma finite case. Okay, two. Suppose mu is sigma finite. Okay, mu and sigma. Mu is also sigma finite. Suppose. Let's assume mu sigma finite. Then the choose we will have two sets. I mean x equal to union of xn equal to union of yn. Okay, such that mu of xn is finite and mu of yn is finite. Then xn intersection yn will increase to x. Okay, and there you will get the derivative. Okay, and then the restriction. I mean because of uniqueness. See, you will get a function that get fn for mu restricted to xn intersection yn. Okay, then fn equal to fm if n is greater than or equal to when you fn restricted to m intersection yn equal to fn if n is greater than or equal to m due to uniqueness. Okay. Okay. Then you have a well-defined f, you get that f. Okay.
Sir, what is Fn here again?
Say it again.
What is Fn here again?
You get a Fn, Radon, not Fn, Hn. Whatever, get the Radon Nykodym derivative for that. See, in the proof, you get a H, no? I mean, this is just trivial. I should leave it as exercise. If you prove it for finite,
Okay,
then you can prove it for sigma finite. You take an increasing union of sets where it is finite and get a Radon Nykodym derivative for each n. Okay, and they are well defined. I mean, they are consistent. If you take a bigger set, then the restriction is the Radon Nykodym derivative of this. I mean, it's all up to almost everywhere. It's because of the uniqueness of the Radon Nykodym derivative. Then you get a single H which satisfies the condition. Okay, this is, I should leave it as an exercise, but it's clear. Okay. Okay. Now we have seen that, so I want to say something else, which I have, okay, anyway. So this is second or third, second remark. The remark is, if you have a lambda which is less than or equal to, lambda is dominated by nu, okay, then you have the Radon Nykodym derivative of d nu by d nu, okay, and then you have d lambda by d nu, and that should be equal to d lambda by d. I mean, these are all functions, of course. These are all functions which are almost everywhere defined. Okay? And this is just clear because, I mean, it is just you write the definition, and this function, this whatever you multiply will satisfy the condition, and by uniqueness it will follow. By uniqueness. Okay? Is it fine? It will follow by uniqueness, right? Is it clear? See, this will satisfy this condition, no? You integral of any f of d d lambda
Sir,
by, yeah,
So these equalities are in almost everywhere.
everything is almost everywhere. Even uniqueness is almost everywhere. So these equalities also almost everywhere. When we are dealing with measure theory, it's all almost everywhere. Uniqueness. Okay? There is no, I mean, there is no meaning to talk about. It's a function is L1. Okay, so it's defined almost everywhere. I mean, whatever we do, it's up to almost everywhere we consider. Okay? So this is clear to everyone. You just substitute it. I mean, anything. See, if we have two measure, nu and mu. Suppose nu u equal to some h d mu. Okay, then this h is the Radon Nykodym derivative for nu with respect to mu. So suppose if we have two measures, so suppose h satisfies this for nu, and suppose lambda of some e equal to some h1, this is h2 with respect to d nu. Okay, then lambda, this is equal to integral over h2 h1 d mu, right? So because of that, you just apply the, see, if you have a Radon Nykodym derivative, it's not just it satisfies this condition, it satisfies this condition. If something is Radon Nykodym derivative, f d nu by d mu, okay, of d mu, this is a function, okay, this is not you cannot just cancel it like that, it's just a function, d mu is equal to integral f d nu, okay, it satisfies this. In particular, it will satisfy for the Radon Nykodym derivative d lambda by d nu. So you just substitute it, you get that. Sorry, here it will be here it will be. Okay. So that is why this equation is true. It's fine. Anyway, you convince yourself. It's all very simple, easy thing to do. So then there is something called, I mean, it's a very easy exercise, but I want to leave it as an assignment, which is an exercise in Sundar's book. So, which is this assignment? Okay, exercise 7.3.4, which I leave it as an assignment. Okay. So, which deals with the complex measure. So, if you take complex measures, or if you take signed measure, then that involves two positive measures. It's a difference of two positive measures. Okay. Suppose if that is absolutely continuous, you can take by taking, I mean, then by carefully analyzing, you can see that both those measures will be absolutely continuous. Both those positive measures will be absolutely continuous. So there will exist two positive function, but when you take the difference of that, you will get a real valued function. So if you have a signed measure and a positive measure, then you have a real valued function which will satisfy this condition instead of a non-negative function. So now you have a complex measure and its total variation measure. Then any complex measure is absolutely continuous with respect to its total variation measure. Okay. Now you get a function, complex valued function, G, which satisfies that. Now you consider mod G for that. I mean, G is the Radon Nykodym. See, if you have a complex measure, mu is a complex measure. Okay. Then you take mod mu, which is the total variation measure. This complex measure mu is absolutely continuous with respect to mod mu. Okay, this is a positive measure. So we will get a G such that integral G d mod mu equal to mu. Okay, is given by this. Okay. Now we consider this mod G. Now you take mod G d mu. Okay, or something like that. So yeah, mod G d nu. This will give a new measure. Okay, which it's a positive measure. But then you can prove that this will have mod equal to 1. I mean, when you have just signed measure, this will have mod equal to 1. And using that, you will get the Hahn decomposition, which yesterday Divya proved. Maybe not many people followed it, but this gives a proof. So you just take, using this G for a signed measure, not complex measure, you take this G, mod G will be equal to 1, which you have to prove. I mean, which is not very difficult. You can directly look at it. G of 1 and G of minus 1 you take. Okay. This will give a set. This will give a set. And there, in this set, the signed measure will take the value, positive value. Here it will take the negative value. Okay. Whatever I am saying, if you don't understand, look at the exercise. It will be clear. Okay. So I want you to, straightforward exercise. So I want you to go through that. I mean, write that as an assignment. Okay, that's an assignment. So the number I have given, you can, I will send the notes anyway, so you can look at it. So it's 7.3.4. Okay? And then you write the Hahn decomposition, which follows immediately. So which is the proof? He gave a different proof. I'm not sure where he used it anyway. So yesterday he didn't use it for the duality. But anyway, he gave a proof. So this is an easy proof of that. Okay. Okay, so this is Hahn decomposition. How much time I have? So I have some more time. So next I will prove what is called a Lubric Nykodym theorem. Okay. Another theorem. Okay, so this says the following. Suppose if we have two measures or finite positive measures, on some set. Okay. Okay, then so if you have any measure, any two measures, mu and nu, okay, then one measure can be decomposed with respect to other measure as sum of two measures, where one of the measure is absolutely continuous with respect to that. So there is another remark which I forgot to say. I mean, see, you can say that some mu is absolutely continuous with respect to nu. The nu can also be absolutely continuous with respect to mu. Maybe I'll finish that and come. Which is anyway, it's in the book, everything. So we have denoted if nu is absolutely continuous with respect to mu, and suppose, and mu is also absolutely continuous with respect to nu. Okay. Then d mu by d nu is greater than 0 almost everywhere. Okay. And d nu by d mu equal to d mu by d nu inverse, just 1 by 1. This is just clear because suppose if it is equal to 0 somewhere, then you will get a set where, I mean, on a set of positive measure, then on that set, one of them will have non-zero measure, the other one will not have non-zero measure. It's clear. Okay? It has to be strictly greater than 0. Okay? We have the relation between mu and mu of E. Mu of E equal to the Radon Nykodym derivative d mu by d mu. Sorry, d mu by d mu. That again, mu by d mu, right? So I'm saying that if they are mutually absolutely continuous, this is what is mutually absolutely continuous. Okay? What is called mutually absolutely continuous. This is what is called mutually absolutely continuous, and it's denoted by mu is absolutely continuous with respect to mu. Okay? So if they are mutually absolutely continuous, that means if mu of e equal to 0, if and only if mu of e equal to 0. I mean, this is mu is less than mu means if mu of e equal to 0, then mu of e equal to 0. And the other way is also true. So if mu of e equal to 0, if and only if mu of e equal to 0. If they are mutually absolutely continuous, then if this Radon Nykodym derivative cannot be equal to 0 almost everywhere. Suppose if it is 0 on a non-zero measure set, okay, then on that set mu of e equal to 0 and mu of e, right? Mu of e equal to 0, but mu of e is not equal to 0. What does it mean? Yeah, so it will not be, yeah, exactly. Mu of e equal to 0, but mu of e is not equal to 0. So it's not the other way. This condition will be violated. The second condition will be violated. Okay? So because of that, the Radon Nykodym derivative has to be strictly positive. Then you can take the inverse, and that is the Radon Nykodym derivative of mu with respect to nu. Okay. Okay. So this I think.
Sir, this is the like function in use.
This is the function. Yeah. This is the what did
This
you?
is the inverse interval.
Yeah, inverse 1 by that. Yes. 1 by. I mean, it's just a function. 1 by that. Okay. Just the. That's why I need this condition. It is strictly greater than 0. It's not equal to 0. Then you take the reciprocal. It's just the reciprocal. Okay. Okay. So I will go through the next theorem. Okay. So here it is just so. Okay. So if we have mu, two measures, two finite positive measures on some x f, then mu equal to mu1 plus mu2, where mu1 is absolutely continuous with respect to mu, and mu2 is orthogonal to mu. What is orthogonal to mu? Which is in the which is in the exercise, it's in the Kahn decomposition. What we mean by orthogonal to that is this x will split into x1 union x2, and mu of e equals 0 for all e contained in x1, and mu2 of e equals 0 for all e contained in x2. Okay. I mean, it's positive measure. So mu of x2 is, I mean, it's enough that it's not real measure. So mu of x1 is 0 and mu of x2 is 0. They are supported in disjoint sets. Okay. This means that mu2 and mu are supported, whatever it means. This is what is called support. The complement has measure 0. Okay. Supported in disjoint sets. Okay. Okay. So this is the theorem. The theorem says if you have two measures, mu and nu, then the nu can be split into two measures. I mean, nu can be written as sum of two measures, mu1 plus mu2, where mu1 is, and the first one is absolutely continuous with respect to mu, and the second one is orthogonal to them. Okay. Mutually orthogonal to them, and mutually singular or whatever. This is what is called singular. Mutually singular. Okay. Okay. So, like the same way, you write rho equal to mu plus mu. Okay. Okay. Then clearly both this mu nu, they are absolutely continuous with respect to this because it's positive. So there exists a g by g equal to d nu by d rho. Okay. We take this Radon Nykodym derivative. Okay. Now because by whatever the argument we have done as before, okay, this G is positive, and also G is less than or equal to 1. Okay? I mean, it's not strictly 1, but there's no absolute continuity between mu and mu. So it can be less than or equal to 1. It's clear, okay, because it's a bigger measure, so it is less than or equal to 1. Now you take x1 equal to G inverse of singleton 1, okay, and x2 equal to x minus x1. Okay. Now on this x, so I want to prove that on x1 mu and rho will coincide. Okay, and here and nu1 or nu I equal to 1 xi g. Equal to, I mean, using that integral or whatever. It is just 1 xi g. Or I'll take this. Gi equal to 1 xi g. I equal to 1. And nu1, nu2 be such that d nu1, d nu I by d rho equal to Gi. Okay. Okay. Now you can see that these things will be satisfied by that. So we have got two measures, nu1 and nu2. Now it's clear that I mean x1 union x2 equal to x, and nu1 is concentrated in x1. Okay? Nu1 is supported, nu I is supported in xi by definition. Is this okay what I am doing? Because I don't see anyone, so I hope it's fine. Okay. So nu I is concentrated in xi. Okay. So they are concentrated in disjoint set. They are anyway mutually singular with respect to each other. Okay. Nu I is supported in xi, and nu equal to nu1 plus nu2 because G equal to G1 plus G2. Okay. Because of that, G is just the Radon Nykodym derivative of nu with respect to rho. Okay. Since G equal to G1 plus G2, okay. So nu looks like this, nu1 plus nu2, and on x1, okay, the Radon Nykodym derivative of nu1 with respect to rho is 1. So on x1, rho and nu1 coincides. Since d nu1 by d rho equal to 1 x1. Correct? Because G is 1 on that. I mean, we have taken G inverse singleton 1 as x1. So G is 1 on x1. Okay? Because of that, we have d nu1 d rho equal to 1 x1. So they coincide. So mu of E equals 0 for all E contained in x1. Okay? That is, mu is singular. Mu is orthogonal to nu. Mu is supported in x2. Okay? So mu is orthogonal to nu or singular with respect to nu. On the other hand, if you take any if you have any E contained in x2, okay, and mu of so we want to prove that nu2 is absolutely continuous with respect to mu, right? So suppose mu2 is 0. So mu of E equals 0. So suppose if you take mu of E equals 0, okay. So this implies that mu of E equals 0. So G is strictly
Sir,
yeah.
um, sir, you have written that mu of E is 0 for all E subset of x1, is it?
Yes, yeah. This is earlier. Yes, right.
Yeah, sir. But doesn't that imply?
Huh?
Yeah, sir. But doesn't that imply mu and mu1 are mutually singular?
New one. No, new one. No, new equal to new one on x1. New we have decomposed as new one in x1 and new two in x2. So new one and new two are singular. I mean, we have two sets. X looks like x1 disjoint union x2. Okay, and this is new one is supported in x1 and new two is supported in x2. They are disjoint set. And this
Yeah,
is
sir.
their sum is new. What do you mean by new one are singular?
Sir, you have concluded that mu of E is 0 for all E subset of x1.
Correct.
Therefore, mu is mutually mu and mu1 are mutually singular according to what you have written.
Mu and say it again. Mu and new one are singular.
Sir, you have written that at least.
Oh, I have written something else. Okay, that is possible. No, I have written mu and new one. No, where I have written something.
Yeah, but
The-
aren't we supposed to get
No,
mu less than equal to new
oh,
one?
are you? No, what is the problem? I have interchanged new one and new two in the proposition. Okay, is that the problem?
I guess like
Okay, in the proposition I have written mu one and mu two. Maybe mu two
even
and
I'm a bit confused.
is that what the confusion is? The proposition I have new one and new two. Maybe new two and new one you can say. Okay, it's that new two is this and new one is it. Is this fine?
Yeah.
Okay. One of them, I mean, I just want to get one of them singular and another one absolutely continuous. Okay. The singularity we have proved. One of them is singular. We have to prove the other one is mutually absolutely other one is absolutely continuous. That's what we want. Okay. Fine. Okay. So suppose mu of E equals 0. Okay. Mu of E equals 0 will imply. So mu of E equals, so this is correct. I have to erase this. Mu of E equals 0. Okay. This implies, so because rho is mu plus nu, okay, rho of E equals nu of E, right? But then rho and nu are, I mean, they are related through the G. Nu of E equal to integral G d rho, right? Over E, right? But it's also further that for all F contained in GE, mu of E equals 0. Mu of F is 0, sorry. This implies, I mean, again, I should have used that in change it. Mu of E equals 0. This implies for all F contained in E, mu of F equals 0. This implies rho of F equal to nu of f. Okay, but then rho and this are related by this. For all f contained in E. This implies what? This implies 1 f equals g1f, right? Or because this is true for all f, this E equals this. This is true for all f, so this is equal to 1 equal to this. I mean, if some integral over all sets are equal, then they are equal. So because of that, 1 E equal to G1E. Okay, almost everywhere. Everywhere it's almost everywhere. So, I mean, the value of G on the set E is 1. Okay, so the E is, this implies E is, I mean, apart from a set of measures 0, E is actually contained in x1. X1 is the G inverse of 1. Okay, so this implies nu2 of E equals 0. This implies nu2 is absolutely continuous. Is this fine? I'm sorry. These things are not very, does not contain any beauty. So it's just a bit messy. Is this fine? Now the idea is the following. You have two measures, mu and nu. Okay. You want to decompose the other measure nu with respect to mu as two measures, nu1 and nu2, so that one is absolutely continuous with respect to mu. The other one is mu singular with respect to mu. Okay. Now you take the sum of mu and nu, which is a new measure rho. Now you take the Radon Nykodym derivative of this nu with respect to rho, which you call it G. Now you take the set where this G takes the value 1. Okay. On that set the new one, whatever the new one, where you have defined this as the measure on x1, where it takes the value 1. On that mu should be 0 because the new one and the new value and rho value are same. So mu should be 0 on that. So mu is singular with respect to the one of the measure. On the other set, if you have any set, anything there it has to be, suppose mu of E equals 0, then that implies that the Radon Nykodym derivative on that set, the value of the Radon Nykodym derivative on that set is almost surely 1, almost everywhere equal to 1. So that set is almost contained in the other set. So nu2 of that set is also 0. That's all. Okay, you just carefully write it, it's clear. So I think orally I can say it more clearly than say. So further, this is unique. Shall I just leave it? You can just look at the book. Okay, this is the same idea. Okay, so if you have any doubt, you can tell me, because it's this set and other thing. It's very difficult to explain here. I can stop or I can continue for some more time. So I want to prove the Rees representation theorem. Okay, there is some uniqueness involved in this. I asked you to look in the book. Okay, because it's the same idea. You have to repeat. Means exactly the same idea. If there's something is contained mutually that, and it will follow that if you have two measure, then you can show that the difference is 0. The modulus of the difference of the measure is 0 because one is supported here, one is I mean, you will prove that modulus, whatever the nu1 minus nu2 is supported. No. If you have nu1 prime, nu2 prime, then nu1 minus nu1 prime, nu2 minus nu2 prime, they are supported in both the sets which are disjoint. So that has to have measure 0. That's what you do. Okay. Anyway, I don't want to go through that. I ask you to look at the book. If you have any doubt, you ask me. Shall I go for some more time? Next, I want to prove something about Rees representation theorem. So something about C of x, but it will take some 15 minutes. But it's already 6:17. Okay, maybe I'll stop. I'll do next class.
Sir, this theorem is the Lubric-Nykodym theorem, right?
This is Lubric-Nykodym theorem. Yes, correct. Okay. Okay, I will end the session. We'll meet tomorrow. We'll meet anyway. Chaitanya is starting, so we'll meet tomorrow. Okay, bye.